Well, so exercise 7 now. So what this exercise asks us to prove is this. That is, U and V are two ideals in a ring. Then we have to prove that their product, which we came across in the previous exercise, is actually contained in the intersection of U and V. So basically we have to just show that any element in this set is also in this set. So we take start off by considering an arbitrary element in this set UV. So let A1 B1 plus A2 B2 etc. plus A and Bn belonging to UV B any element where you know the condition, these AIs belong to U and the PIs belong to V. Bn belong to V. Okay. Now, since U is an ideal, we have A1 B1, A2 B2 up to A and Bn. Now all these elements belong to U. Why? Because see, all the AIs are in U. Now we are multiplying each AI by Bi, where we can consider Bi as an arbitrary ring element. So the fact that U is an ideal tells us that these products will all belong to U. And hence their sum also belongs to U, because U is an additive subgroup. A and Bn belongs to U. Also, now note that we can carry out a similar argument with V in place of U, because V is also an ideal. And that's what we are going to write now. Also, since V is an ideal, we have the same products all now belonging to V, because now the elements B1, B2 etc. to Bn, they are elements in V. So each one of them, they are being multiplied by AI. Bi is being multiplied by AI from the left. So if we consider AI as an arbitrary ring element, then AI Bi should be in V. So all these products are in V. And so their sum is also in V, because V is an additive subgroup. Thus, this element now, it belongs to U as well as V, so it belongs to their intersection, U intersection V. And this proves the thing that we wanted. And there the solution ends. Right, then we look at this one. It's about a particular ring. Now, leaving general rings, we are now going to consider the ring of integers. Our first example of a ring. So this is exercise 8. Let R be the ring of integers and let U be the ideal, or they have written set ideal. All multiples of 17. Okay. Prove that if V is an ideal of R, and satisfying same thing, satisfying these containments, R contains V and V contains U. Then either V is equal to R or V is equal to U. And at the end of this exercise, they asks us to generalize this result. Okay. So we are given the ring of integers and also the ideal of all multiples of the integer 17. Is that an ideal? Actually, it's an ideal. It's not very difficult to see why. You see, we have the ring of integers R, and we may denote this set by 17R, so which is nothing but all the multiples of 17, integer multiples, where m is any integer. Now you can easily check that this is an additive subgroup and it also satisfies the second condition for an ideal. So I am not going to do that. That is also not something that has been asked here. We are rather supposed to prove something else about Q. If another ideal V is given in the ring of integers which sits in between U and R, then this V has to either be equal to R or U. That's what we have to show. So let us proceed towards the solution. Okay. Let V be an ideal of R such that V contains U and V is not equal to U. That means the situation is now this. If I draw a quick Venn diagram of the situation, the ring is this set. Now in it I have U, the ideal of all multiples of 17, and I have drawn the U unnecessarily big. Let this be V and let this be U. Okay, so this is the situation, and additionally this is already given to us here as the condition of this exercise. Additionally, what we are now assuming is this, that our v is not equal to u. If v is equal to u, then of course there is nothing to show, because that is one of the conclusions. But if v is not equal to u, then we have to show that v is actually equal to R, the whole ring. An ideal cannot sit properly in between u and R. That's what we have to show. Okay. So now, since we have assumed v to contain u, but at the same time not being equal to u, there will be at least one element in v which is not in u. So we can choose an integer, because after all we are working with integers, let's not forget that. So we can choose an integer m belonging to v minus u. Okay. Now recall what u is. U is the ideal of all integer multiples of 17. So that means our m is not an integer multiple of 17. Or in other words, 17 does not divide m. Then m does not belong to u, and so 17 does not divide m. Now recall a property of, note that this number is a prime number. This 17 is a prime number. If we are given a prime number and another integer, then exactly two things can happen. Either the prime number divides the integer, or the prime number and the integer are relatively prime. In fact, we have seen this when we discussed integers. So now it is given that 17 does not divide m. So since 17 is prime, so 17 and m must be relatively prime. They should not have any common factor between them other than 1. Okay. Since 17 is a prime number, this implies that 17 and m are relatively prime, that is their greatest common divisor is 1. Recall that this is the notation for greatest common divisor of two integers in Herstein, in this book. Hence, and we also know what happens when we have this condition. Hence, there exist integers a and b such that 1 is equal to 17a plus mb. That is, the GCD of any two integers is a linear combination of the integers, where or rather we can say integer combinations, because the numbers by which we are multiplying, they are also integers. Okay, so we have got this. Now (17a) belongs to u, because it's an integer multiple of 17. By definition, u is the set of all such integers. So 17 belongs to a, which implies, 17a belongs to u, which implies 17a belongs to phi. Why? Because u is a subset of phi. And MB belongs to V. MB also belongs to V. Why? Because M is in V. It's not in U, that is something else. But after all, it's an integer in V and V is an ideal. So because of the fact that V is an ideal, multiplying this ideal element by an arbitrary ring element gives me again an element in the ideal. Okay, and MB belongs to V. Since we can write the reasoning brackets, since V is an ideal and M belongs to V. Okay, so both these integers 17a and MB are in V. MB is in V, 17a is also in V. So their sum will also be in V. Hence, 1 is equal to 17a plus MB belongs to V. Now note what we have got here. We now have the fact that the unit element in the ring, which is nothing but the integer 1, belongs to this ideal V. So by the first exercise, we can now conclude that V is equal to R. Hence, or thus, first exercise, we have V is equal to R. So that's what we wanted to show. Either V is U, or if that is not the case, then V is R. So there are only two possibilities. And now note one more thing. In carrying out this solution, we have used the fact that 17 is a prime number, but we have not used anything else about the particular number 17. The fact that it is 17 actually does not play any role in this solution, in this part of the solution. Only the fact that 17 is a prime number plays a role here. So now this part we have been asked to generalize. Now it's clear. In place of 17 we can have any prime number. So we can write that in another paragraph. Note that we can replace 17 by any prime number and both the claim and the above solution work. So that is the generalization, and the solution ends here. Then we turn to the next one. This type of ideals which do not allow any proper ideal to sit between them and the whole ring have a name. They are called maximal ideals. They are very important. In fact, in the very next section, we are going to see something about them. You see, we have just now I said maximal ideal, right? So in the ring of integers, ideals which look like this, PR, where P is a prime number, they have that property that in between the ring and such an ideal, nothing else, no other ideal sits properly. Now what happens, since PR is an ideal and R is the ring of which PR is an ideal, we can form this quotient ring, right? This quotient ring has a particular property. We will see this in the next section. Okay, so let us now go to the next exercise. exercise 9. So we again go back to general rings. If U is an ideal of R, let RU be the set of all elements X in R such that XU is equal to 0 for all U in U. Okay, so we have now defined, we are given an ideal U in a ring R, and using that ideal we have defined a set in the ring. Now naturally we will be asked to prove that this is an ideal. Prove that RU is an ideal of R. So we follow the standard procedure. We will show that RU, first of all we show that RU is a subgroup of R under addition, and then we will look at the second condition for an ideal. But at the same time, make sure first that RU is non-empty. We have already discussed it in the previous video, or I think the one before that. To see that quickly, you just have to produce an element in RU. Okay, by the way, what is RU first of all? It is the set of those elements in the ring which, if you multiply by any element in U from the right side, okay, this direction is important, then it becomes, that product becomes 0. Not that XU may not be equal to UX, because it's not given that the ring is commutative. So we have to keep in mind that it's XU. We are multiplying the element X by elements of U from the right side. And note that this has to be true for all elements in U. Then only that X will belong to RU. That's the definition of RU. So there is a very easy element. There is an easy element in RU that you can think of, which is nothing but the 0 element. Why? Because if we take any element in U and multiply 0 by that element from the right side, then we get 0. This is from the fundamental lemma that we started with, that this type of calculations in ring, that is, you multiply 0 element by any element, you get the 0 element back. So that means 0 belongs to RU, and as such RU is a non-empty subset of R. Okay, so now we start showing, first of all, RU has to be shown to be a subgroup of R under addition. So let X and Y belong to RU. Okay, so we have taken two elements in RU, and at the same time let us also take an element in R. Okay, then XU is equal to 0 and YU is equal to 0 for all U belonging to U. This is just the condition for X and Y to be in RU. Since they are in RU, so this is true. Hence, X minus Y times U in our ring, this turns out to be equal to, using all the ring theoretic properties, xu minus yu, which is nothing but 0 minus 0. So this is also equal to 0 owing to these things, these two things, conditions. This for all u belonging to u. This implies x minus y belongs to Ru, and hence Ru is a subgroup of R under addition. Okay. So now next we have to prove that XR and Rx, both these elements are in Ru. That will complete the proof that Ru is an ideal. Okay. Next. So XR. So that means to prove that XR belongs to Ru, what do we have to show? We have to show that if we multiply XR from the right side by any element u of u, then we get 0. This is what we have to prove. But let us prove the other thing first. Let us first show that Rx belongs to Ru. Okay. Next, we have Rxu. This u, you know, we are going to take it to be any element of the ideal u. By the fact that multiplication is associative, we can write it like this: Rxu. And since xu is equal to 0, so we have R0, this is equal to 0 for all u in u. For all u belonging to u. Hence, Rx belongs to Ru. Oh, sorry. Ru. Now we move to XR. Also, for any u belonging to u, we have Ru belonging to u. Why? Since u is an ideal. That's why, because we are multiplying this u element, small u, by an arbitrary ring element R. Note one thing carefully, that although we are saying here that u is an ideal and it's given that u is an ideal, that means a two-sided ideal, we are not using the fact that u is an ideal fully. I mean, we don't need everything. We just need the fact, we are using the fact that the element u in u is being multiplied from the left by a ring element. Okay, keep this in mind. We will need this in another exercise later on, this fact. That is, we are not using the fact that u is an ideal fully here. We only need one of the two conditions. Okay, so Ru belongs to u, and hence XR u. this is equal to, again using associativity of multiplication, I can write it like x RU. Now note this, since RU belongs to U, and if I multiply x by any element of capital U from the right side, I get 0. So that means here also I am multiplying x from the right side by this element RU of capital U. So this also has to be equal to 0. And this tells me that XR also belongs to RU. Therefore, hence RU is an ideal of R. And this completes the ninth one. Then 10. Exercise 10 is also something similar. We consider a subset in a general ring and show that it's an ideal. If U is an ideal of R, let, now this one has a different notation. I don't really know what these notations, there must be some reason for calling this RU. Okay, I think when we will study about ideals more deeply, then we will come across the reason for these notations, the reason that they look like this, okay, why they look like this. So this is the set of those elements in the ring such that Rx belongs to U for every R in R. It's a slightly different one. Now Rx is not equal to 0, but Rx belongs to this ideal U for every R belonging to R. Okay. Prove that this is an ideal of R containing U, that contains so here not only do we have to show that this is an ideal, but we also have to show that this ideal contains U as a subset. Solution. The beginning is the same. You have to first show that, or you have to convince yourself that this is non-empty. So the thing you try to see is that the 0 element belongs to RU. Trying to show that the given set is non-empty, you always think of this only, because after all, whatever happens, to show that a given subset is an ideal, it anyhow has to be shown that it's a subgroup, and subgroup always contains the 0 element, so you try to show this. Now see if we can put 0 in place of x here. That is this true? R0 belongs to U for every R. Okay, in fact, let us just incorporate this in the solution itself. note that since it's not that straightforward, we have to at least say something. So let's write this in the solution itself. Note that r times 0 is equal to 0 and 0 belongs to u. Because u is an ideal, so u is a subgroup of R under addition, so it has to have 0. So this belongs to u, and this is true for every ring element R. For every R belonging to R. Hence, 0 belongs to this subset, and consequently this is non-empty. Okay, so non-emptiness has been shown. Now we show that this is a subgroup of R under addition. So let's consider two elements, or let us take all the necessary elements now itself. Let x and y belong to this and R. Okay, we will meet R in the definition itself. So let us consider a different type of element. Rho be any element